Now, the calculation will give you a power of 10 to the minus 7 meters. That is the order of power of a wavelength for visible light. Often we quote answers for visible light, for the wavelength of visible light in nanometers, rather than in order of 10 to the power of minus 7. So I've rearranged the order of power to have 10 to the minus 9, which is nano, and that gives 486. So 486 nanometers is the wavelength. And that is the wavelength that will be emitted when a electron de-excites from the fourth level to the second level. So if we go up to the energy level, the line spectra, now written in right next to each line, what each line represents. So this red line represents when an electron de-excites from n equals 3 to n equals 2. The purple line is when an electron de-excites from n equals 6 to n equals 2. We've just worked out a wavelength for when an electron de-excites, of a photon, when an electron de-excites from n equals 4 to n equals 2 and releases a photon. And we worked out the wavelength of that photon to 486 nanometers. Now, just by looking at each one, we can figure out the one in between. So this blue line is a photon released when an electron de-excites from n equals 5 to n equals 2. Using this value here, you can work out the energy of that photon, and then you can work out the difference between these two energies of n equals 5 and n equals 2, and you will end up with the same number. Now, if you note that this side of the electromagnetic spectrum, beyond the blue side, is UV, and this side is infrared. Now, this is the visible part of the electron's de-excitations. We are now going to consider the other sides. So if you look at this energy level diagram here, let's concentrate on these questions later, but we know that from our discussion that all the transitions to level 2 give off visible light. If we look at beyond the blue, we will have a higher frequency, so higher energy jumps. And when an electron de-excites from 2 to 1, 3 to 1, 4 to 1, 5 to 1, 6 to 1, it'll give off photons of frequency in the UV range. And when electrons de-excite from higher levels to n equals 3, they will give photons with frequencies in the infrared region. This is called the Balmer series for the light in the visible part. This is called the Lyman series for the photon transitions into level 1, and this gives us infrared light for de-excitations to n equals 3. This is not specifically on your syllabus, but it's interesting to know what's on either side. Okay, we can't see this, but we can see this region here. So the question is, an accelerated electron collides with an atomic electron of hydrogen in its ground state. So the electron sits here, another electron comes in, hits it, and transfers 2.0 times 10 to the minus 18 joules of energy. The electron excites to a high energy state. Which energy level does it excite to? Now, this is all electron volts. This is joules, so we must convert this into joules first. So the energy that is absorbed by the electron sitting at the ground state is 12.75 electron volts. It will excite to, and if you look at the numbers, the difference between the levels that gives 12.75 is the n equals 4 and the n equals 1. So 13.6 minus 0.85, that gives us 12.75 electron volts. So that's the transition and answer to question 1. N equals 1 to n equals 4. We could say excitation from n equals 1 to n equals 4. So the electron excites from n equals 1 to n equals 4. Now the second question is when the electron de-excites from the fourth level, there are a number of transitions. So it could jump from 4 to 3, 4 directly to 2, and 4 directly to 1. That's 3 possible transitions. In addition to that, you have got when the electron jumps to, let's say, n equals 3, it could then jump to n equals 2, then n equals 1. Or it could jump from n equals 3 straight to n equals 1. And when we look at all the possibilities that the electron could transition through, we see that we have 6 possible transitions. Now, in my previous lesson, I taught you a trick to figure this out. If it's from level 4, take off 1 and then do 3 plus 2 plus 1. And if it was level 5, it would take off 1, that would be 4, and be 4 plus 3 plus 2 plus 1. And that will give you the number of possible transitions. The next question is, how does the line spectra validate? So how does the line spectra, which is this, validate this energy level diagram? So that was the link that we've been making through, but we have to write it out in words now. So note the number of times I say fixed in this answer. So each line on the line spectra corresponds to a fixed wavelength. So let me go back up. So each line corresponds to a fixed wavelength with a fixed frequency, and since E equals hf, that means that photon will have a fixed or discrete energy. So each line corresponds to a fixed energy. When an electron so now we're going to jump to the energy level diagram. So when an electron de-excites between two fixed energy levels, so the word fixed is cropped in there again. So not de-excites between two energy levels, we say two fixed energy levels, because for hydrogen, it's the same everywhere in the universe. They release a photon with a fixed energy and a fixed frequency. And these photons are responsible for the lines produced on the emission spectra. This is a very, very common question.